Hey everybody, today I want to talk about another principle in mathematics, sort of explaining what it is and then giving some examples of puzzles that use the principle. So this principle is called the pigeonhole principle. I'm just going to write that out now. Pigeonhole principle. Now this is a very powerful tool in math, especially when you aim to prove some claims. So I'll start by explaining what this principle is and why it's called the pigeonhole principle. So the basic idea is, imagine you have a bunch of pigeons. Let's say you have 5 of them. Let's say that these dots represent pigeons. And you have 4 pigeonholes. And let's say that the pigeons need to each go to a pigeonhole to sleep, right? So it's night time, all these 5 pigeons need to pick a pigeonhole. The pigeonhole principle essentially says that at least one hole will have more than one pigeon. Which should kind of make sense. I mean, there's more pigeons than there are holes. So basically the idea is that, if this one goes here, if they all go to a different hole, which is the only way they won't double up, this pigeon here is going to be forced to join, the other pigeons. Forced to make one of these pigeonholes have an extra pigeon in it. So the pigeonhole principle more broadly says that in any scenario like this, if there are more pigeons than holes, then one hole will have a double up for pigeons. So this should seem like quite obvious and quite sort of trivial, and I'm going to talk about now some applications to the pigeonhole principle where it's kind of less clear how the pigeonhole principle is being used until you think about it. The main problem with these puzzles, the main reason they're difficult, is because you have to really think about what are your pigeons and what are your holes, because they're going to be different in every problem. So to start off with, I can make a very basic claim that if I take 5 cards from a deck of cards, at least 2 of them are going to have the same suit. So let's say, so I have 5 cards. And let's say I have, this is a heart, this is a diamond, this is I guess it's a club, and this is a spade. I don't know, it doesn't matter. This last card, well, it has to be one of the 4 suits, and whatever suit it is, it's going to create a double up. This is the exact same idea as with the pigeons and the holes, but this time the pigeons are the suits, or the suit options, and the holes, the pigeons are the cards, and the holes are the suits. So we can rethink this question as having 4 buckets: a heart bucket, a diamond bucket, a spade bucket, and a club bucket, and we have 5 cards, and each card has to go into a bucket, which basically just means that card has to have the suit, right? And now we rewrote the problem to be identical to this basic example here. So this is an example of the pigeonhole principle where it's not actually obvious what your pigeons are and what your holes are. So here the pigeons are cards and the holes are the suits. Alright, let's get rid of all this, and I'm going to give a couple more examples of this principle. So if I look at the US Constitution, for any string of 27 words in that Constitution, there's going to be at least 2 words that start with the same letter. And that's true for any 27 words. So I'm going to write 27 words at least two of them start the same letter. Now we're going to use the exact same idea here. This time, what are my pigeons and what are my holes? Well, my pigeons are going to be the words, and my holes are going to be the starting letters. So this time I'm going to have 26 holes. So we're going to have A, B, C, D, etc., etc., X and a Y and a Z hole. And for every word out of my 27 words, so these circles can all be words, and keep in mind that there's going to be 27 of them. For my first 26 words, I could put them all in a separate hole, that's fine, meaning they all start with a different letter. But then it's that 27th one again that's going to cause problems. It's going to have to create a double up. So this is the same idea again. But remember, the pigeonhole principle is always going to apply if there are more pigeons than holes. Now that's important. This statement is only true because I said 27. If I said 26, it wouldn't be true anymore because every word could start with a different letter. So here, the words are going to be the pigeons and the holes are going to be the letters the words can start with. Alright, let's keep going and we're going to get more abstract as we go on. Here's another claim. In New York City, there are 2 non-bald people with the same number of hairs on their head. Okay. Now again, this is a very bold statement. And this is another one of those statements where you don't just have to prove it by giving an example, you can prove it more broadly. So, in order to prove this is true, I don't have to actually find the 2 non-bald people with the same number of hairs on their head. That'd be crazy, right? You can't go through New York City and count everyone's hair. But, you can prove this with the pigeonhole principle. So once again, what are our pigeons, what are our holes? Well, our holes are going to be all the possible number of hairs people can have on their head. So it says non-bald, so let's just say they have at least 1 hair on their head. So this is people who have exactly 1 bit of hair. Maybe this is a kid who just had their first hair, whatever. These are all going to be kids at the start. And then at the very end, well, what's the maximum amount of hair someone can have on their head? We'll call that N. So N is going to be the most hairs that anyone in New York City has on their head. And then N minus 1, N minus 2, N minus 3. N is going to be a big number, so let's just say here, let N equal the largest number of hairs someone in New York City has on their head. Cool, and again, what are our pigeons? Our pigeons are going to be the residents of New York City. Now, I'm not completely confident how many people are in New York City, but it shouldn't actually matter. Let's just say there are M people in New York City. Now, I don't have these numbers on the top of my head, but what I do know, and you can verify this online, is that M is greater than N. Meaning there are more pigeons than there are pigeonholes. And again, beautifully, that is all we need to prove the claim is true. So I don't have to actually find the 2 non-bald people, but what I do know is that if every person goes into a different bucket, which tells me how many hairs they have on their head, there's going to be at least 1 double up. So again, this doesn't mean that you're going to be that person with the hair doppelganger, but it does mean that there's going to be at least 1 pair of people with the same number of hairs. Alright, cool. Let's get rid of all that. I think I'm going to get rid of this as well now. I'm going to need some more space. Okay, now we're going to get into some really disguise problems. There's problems that use a pigeonhole principle, but it's really not clear. Let's try this one. If all nodes on a graph G of n have a degree greater than n on 2, then G is connected. All right, this is a graph theory problem. There's a bit of terminology I might need to go over, but don't be scared, it is quite straightforward. So in math, when we talk about graphs and graph theory, we're not talking about these graphs that we're used to in math class, where it's like a chart, f of x, we plot it. A graph here is just going to be a set of vertices, which are, or nodes, you call them whatever you want, I call them nodes, and they're connected by edges. So for an example, this here is a graph. Now when it says G of n, it's just saying that the graph has n vertices. So in this drawing I've done here, n is going to be 5. And the degree of every node is the number of nodes it connects to via edges. So for example, the degree here, I'm going to write them all in green. This node has a degree of 2, degree of 2. This has a degree of 3, it's got 3 neighbors. This is a 2, and there's a 1. That's what a degree is. You can just write dig for short. And finally, G is connected. Now connected is a certain property of a graph that this graph actually does have. And what it means is that you can walk from any node to any other node on the graph just by going on the edges. So for example, I can walk from here to here on the edges, or from here to here. For any pair of nodes on this graph, for any 2 of these 5 nodes, there is a walk between them. Now, most graphs that have any utility to us are going to be connected. So like for example, in any city, or any country really, take New Zealand, at the North Island of New Zealand, that's kind of like a connected graph. So all your cities can be, or even all your houses can be nodes, and then your edges can be roads. And it seems clearly true that you should be able to drive from anything to anything else via the roads. So that is a connected graph, right? For any pair of points, you can connect them. Anyway, so that's our terminology. So it's like, why the hell is this going to be a pigeonhole principle question? It's really not obvious where the pigeons are and where the holes are. But let's go through it. So the first thing we want to do, so we're trying to prove that this thing is true. We're trying to prove this claim is true. So the first thing that I like to start with is to try and get an intuition for why it has to be true, which basically just means try and make it false. And you're not going to be able to, but if you can't, you're going to get a clue as to why. So let's give an example where I have 5 nodes. Now the rule says that every node has to have a degree of half of n over 2. So everything has to have a degree of at least 2.5. So we're going to say 3 is the minimum degree, which means that every node has to have at least 3 other nodes connected to it. And it says here that G is going to be connected. So I'm going to try and make G not connected. I'm going to fail, but we're going to see why I fail. So let's just start by filling out some stuff. So this node here, this bottom right one now has a degree of 3. Now this one has a degree of 3. This has a degree of 3. So far so good. They all have a degree of 3, and my graph is unconnected. But now, I still haven't given this node a degree of 3. And you can see the second that I draw any of these edge lines, I have made my graph connected. Meaning that now I can walk from any node to any other node, which breaks the rule. So it was the introduction of this final node that broke everything. And you might be able to see where I'm going with this, sort of like how it's always the very last pigeon that has to pick a hole that breaks the principle, right? So let's try and prove this more formally. Well, we can't just pick random values for n. We have to prove that it works for all n. So let's start by drawing an example graph with n nodes. Now, connectivity means that for any pair of nodes, there exists a path between them. So I'm just going to pick 2 random nodes out of my general graph and call them node A and node B. And let's just say in the middle here is everything else. These are all the other nodes. So, and then, you know, node A and node B are going to be connecting to some things in here, right? That's the idea. Now, how many nodes are in this big circle, this wiped out bit? Well, it's going to be n minus 2, right? Because the whole graph has n nodes in it. This is one of them. This is another one of them. So there's n minus 2 left. So I'm actually going to draw that again in a slightly different way to make what I'm going to say next more obvious. This is node A. This is node B. And in the middle, we have just dot, 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 n minus 2 nodes. Now, we need to show that no matter what happens, this graph has to be connected. Now keep in mind the rule, everything has to have a degree above n over 2. So let's just say, in the best case scenario, which in this case means we're going to have as little edges as possible, right? So in the best case scenario, A is going to have a degree of n over 2, and B is going to have a degree of n over 2. I understand that technically it should be n over 2 plus 1. It won't actually affect the proof. Again, this is a worst case scenario, so it shouldn't actually really matter. Now, there are two scenarios here. Either node A and node B connect, in which case we've proven it. We've proven that there's a connection between any A and any B. So we're done. Or they don't connect. Now, if they don't connect, that means that A has to connect to n over 2 of these. And B has to connect to n over 2 of these. So A connects to some stuff in here. B connects to some stuff in here. Now A has to connect to n over 2 of them, and B has to connect to n over 2 of them. And now here's where the pigeonhole principle comes in. Let's say, for an example, that I have 12 marbles. I'm not gonna, sure, I'll draw them, okay. And you and your friend both want to pick 7 marbles each. No matter what 7 marbles you and your friend pick, you're both going to at least pick the same marble once, right? Like if my friend picks these 7 and I pick these 7, there's going to be a crossover of some marbles, right? And that's true for no matter what 7 you and your friend pick. It's the same idea here. Person A is picking over half of these nodes to connect to, and node B is picking over half of the nodes to connect to, which means that there have to be some overlap. And this is the same as the pigeonhole principle. In this case, the pigeons are actually the edges and the holes of the nodes. So yeah, so with that, we basically have this idea that A and B must both connect to at least one of the same nodes. Let's call it this one. It doesn't actually matter. So we know now that A has to connect to this one and B connects to this one. Therefore, there is a walk or a path from A to B. Therefore, G is connected. And that completes the proof. But we needed the pigeonhole concept to prove this. Alright, I'm going to do one more, and then we're all done. So I'm going to do my final pigeonhole problem. Now this one, feel free to pause and try it yourself, because it is actually quite a fun one. Consider the infinite lattice grid on Z2. So an infinite lattice grid just means a grid of integers, or a grid of pairs of integers in 2 dimensions. So here it's going to be basically the set of all pairs of integers. So for an example, we're going to include 0, 0, 0, 1, 0, 2, 0, 3. We're going to include all these ones as well. Right, all these ones. So every point represents a pair of numbers. I think I spoke a little bit about lattice grids in my video on Cantor in the infinity video, but we're going to have to redraw it again. I'm just going to do a couple of them. It doesn't actually really matter. The idea here is that this is going to go out for infinity in every direction. Now the question is, consider a 100 coloring on the grid. Prove that there exists a rectangle with monochromatic corners. A 100 coloring just means that you have to give everything 1 of 100 colors. So I'm not going to draw 100 colors, but basically each of these points gets a different color. If you want, we can think of it as like a label. So like, for example, this might have label 1, this one might be label 93, this one might be 17. It doesn't matter. In math, we just call these different colors. So 100 coloring, where every point has a different color, or has 1 of 100 colors. Prove that there exists a rectangle with monochromatic corners. What that means is that I'm saying that somewhere on my grid, there's going to be 4 points, like in a rectangle formation, such that they all have the same coloring. So this color equals this color equals this color equals this color. So yeah, this is a pretty tricky question. So firstly, what it means is that there has to be at least one color that's being used 4 times, which we know is true from the pigeonhole principle, because there's an infinite number of nodes here, right? So if there's 400 nodes, then at least one color has to be used 4 times by the pigeonhole principle. That's like having 4 pigeons in one hole. But that's not going to help us at all, because we have to actually prove that they exist in this rectangle formation. So let me try and explain the proof. We're going to start by looking at a 2D version of the proof to make it more simple. Imagine just one line on my lattice grid, and it's going to go on forever. It's just, sorry, not forever. Let's say that it's got 101 colors. Oh, sorry, 101 points, I should say. If every point has a different color, if this point has a 100 coloring, that means that at least 2 points are going to have the same color by the exact same logic. So here, my 100 colors are kind of like my pigeonholes, and the points themselves are like the pigeons. I could give my first 100 points all a different color, but then this final point is going to have to double up the color. So if I have a line of 101 colors, of 101 nodes, there's going to be at least 2 with the same color. So let's keep that in mind. So we've sort of proven like a one-dimensional version of the puzzle now. Now we have to take this and put it into 2 dimensions. So think about this line of length 100. Now, how many lines are there of length 100? How many lines can there be like this? How many lines of length 100 are there? We're getting a bit into combinatorics here, but the question shouldn't be too hard. Well, for the first dot, I've got 100 options for a color. And for the second dot, I've got 100 options for a color. For the third dot, I've got 100 options for a color. So the answer is going to be 100 to the power of 101. It's a huge number. This is the number of different 1D lines that I can make of length 101. Now here's the beautiful part. Because the lattice grid is infinite in the up and down direction, I know that at some point, by the pigeonhole principle, that there's going to be a repetition of one line of length 101. that's in line with the one above it. So just, you know, imagine this is only 101 wide. It doesn't actually matter. The idea is that if I go high up enough, I'm going to come across a repetition. And that's because if there's infinity lines as I go up, that means there's more than 100 to the power of 101 lines. So this time my pigeonholes are going to be kind of like the different combos of colors, which means that there's going to be 100 to the power of 101 pigeonholes. And my pigeons are going to be like each specific line that has to take on one of these 100 to the power of 101 different forms. And I know that I have more than 100 to the power of 101 pigeons. So let's just say that, well, technically it's going to be infinite, but let's just say that I have 100 to the power of 101 plus 1 pigeons, right? let's say I just need to only check this amount. And when I check this amount, there is guaranteed to be a double up. So, by the pigeonhole principle again, that means that we're going to have two lines that have to exist in the same bucket, and those two lines are going to have the exact same form. Now, those two lines that are identical are both going to have at least two at the same point because of this idea of the original pigeonhole problem, where there's 101 holes but there's 100 pigeons. Sorry, 101 pigeons but 100 holes. Which means that on this line, so let's say I have a line of length 101, dot dot dot, and somewhere very very far below or above it I have the same line again. So these lines are both going to be 101 wide, and the gap between them, it doesn't matter how big this gap is, but it can be huge. It could be, let's say it could be 100 to the power of 50. It doesn't matter. They're very very far apart. Because the lines are identical, there exist at least 2 points that are the same on this line, and because the lines are identical, they have to be replaced. They're also there at the bottom. And this forms a monochromatic rectangle. So this question is really interesting because it basically took this pigeonhole principle and it used it twice. Once to get repetition on my line, and then once again to get repetition on all the sets of lines through my space. Now, a reasonable question somebody might have is, can I abstract this into a third dimension? And you actually can. So this claim would also be true on the lattice grid in Z3, which is basically the set of all like rectangular prisms. There's going to be a rectangular prism with 8 monochromatic corners. And this is going to be the same thing in the fourth dimension with a hypercube with 16 corners that are all the same. You can keep doing the pigeonhole principle over and over again, sort of inductively. But the three-dimensional case is too hard to draw, so I did a two-dimensional case. Yeah, but that's basically all I have to say about the pigeonhole principle. It comes up a lot in life. For example, I think I said before, I play a lot of poker. That fact about the 2 suits being repeated in 5 cards actually can matter sometimes in poker, because that's what the board, when you play Texas Hold'em, the board's going to have 5 cards up on it. So you can now say for a fact that at least 2 of them have the same suit. I don't actually know how that helps that much, but you know, these are things that are true. And we can know that they're true because of the pigeonhole principle. So yeah, try and find examples of this in real life. They're everywhere, but I think that'll be the end of the video. So yeah, cheers for watching guys, thank you.